So today, this one is lecture number 32. In this lecture, we will discuss in detail about orthogonal transformation and least square approximation. Here, what we will see that we know that orthogonal transformation, it is a linear transformation. So definitely there is a general method to find matrix of that transformation. But due to this orthogonality, we will have to a specific approach, or you can simply say that very simple approach to find matrix of a given orthogonal transformation. And least square approximation is very interesting when you are coming to find that your system is inconsistent. Then you are looking for best solution. That solution is not a exact solution, but we are looking for approximate solution. So among the several possible approximate solution, we will look for best solution that would be given by least square approximation. And also it is playing very important role in regression, especially when you are having a collection of data and you are willing to uh, put a hypothetical function that one is giving best explanation of the given data. Then in that case, least square approximation is playing very important role. Or simply you can say that curve fitting. If you are having data and you try to fit a curve among those data, then least square approximation is directly giving a solution, directly analytic solution directly you will give. So that's why it is a pure linear algebra concept, but it is an optimization problem. So here you are solving an optimization problem with the help of linear algebra. So when you apply linear algebra, you might have already seen that you don't need to apply calculus concept like gradient and Hessian kind of things. That means first order derivative, second order derivative. You don't need to do those kind of things here. Directly apply the concept of linear algebra, and with the help of that, we will try to uh, know about how to find best approximate solution of a given data, or best approximate function which fit the data. So coming to outline of my today's lecture, first I would like to discuss about recap of orthogonality, that few more concepts that we have to recall in process to make further concept looks easy. So, and in today's lecture especially we will discuss about least approximate solution and least approximation function. That means the function which is giving a better fit of the given data set. Apart from that, also I will talk about matrices of orthonormal orthogonal transformation. So I will discuss that thing as well. So here I would like to mention a matrix of orthogonal transformation. So simply I will write it in short form OT. And at last, if time permit, then I will go to talk about some example from data fitting. And there is a, if there is a noisy kind of approximation function we are getting, that that concept it is coming directly in data fitting. And if you are getting an exact fit, then that concept we are calling it interpolation, or simply you can say that interpolation it is just parameterized version of data fitting, or something more. You will also learn those things in machine learning courses as well. So especially these things are always coming in machine learning concepts. So from that perspective, also you can look into. If you are very good in linear algebra, then visualization is really interesting. So coming to recap of orthogonality. So first, I would like to discuss. I will recall fundamental theorem of linear algebra. I had already told during the discussion of fundamental theorem of linear algebra that we had already discussed only two part of the fundamental theorem of linear algebra. First, it was uh, regarding Sylvester law, rank nullity, and second was orthogonal complement. So here, how to define the fundamental theorem of linear algebra in a complete sense, because now we are having idea of orthogonality, so we can discuss all the three part of fundamental theorem of linear algebra. So we considered subspaces. Suppose we are taking a matrix R3 from R3 to R3 in such a way, null space of the matrix is a line. That means null space of a matrix is a one-dimensional subspace, because line is having only one direction, and the row space of A, that means column space of A transpose, that one is a plane. That means it is having two directions or two basis element. Then we can talk about fundamental theorem of linear algebra. What does it say? First, it is talking about sum of dimension of null space plus dimension of row space of A. It would be equal to dimension of the domain space. What is the dimension of domain space? R3. R3. So what is the dimension of R3? R3 3. So that's where this law we are calling it Sylvester law. There is one equivalent version is that if you write in term of codomain, if you try to look into codomain, so in codomain what structure you will get of Sylvester law? It will talk about dimension of null space of A transpose. That means left null space. Dimension of null space of A transpose plus dimension of column space of A. Another part of intentionally I am not writing. Both are very much similar, so that's why I haven't written. But here again I am writing it. So dimension of column space of A, if you sum it up, it would be equal to dimension of codomain space. Because why? Because you observe null space of A transpose and column space of A where in the codomain space, but where but null space of A and row space of A, where do you observe? You observe in the domain space. So that's way. So both here domain and codomain space both happens to be R3. So that's way it looks very simple. Now, what was the second part of fundamental theorem? It is talking about if you are taking a subspace in uh, domain. So this row, if you are taking row space, then row space always happens to be perpendicular to null space of A. Row space happens to. So that's way. If V is row space of A, then V part would be null space of A. So this one is talking about second part of fundamental theorem of linear algebra. Similarly, you can this you observe where? This you observe in domain space, and similarly same form you can observe in codomain space. What would be in codomain space? In codomain space you are having column space of A, or you can simply say that uh, range of A. So column space of A, and what is another null space in codomain? That one is null space of A transpose. Transpose. That another name of that we are calling it left null space of A. So this would be perpendicular to column space of A would be perpendicular to null space of A transpose. This happens where? It happens in codomain space or target space. This one was the second part of fundamental theorem of linear algebra. Now, third part of fundamental theorem of linear algebra, I had already mentioned that. I would like to recall it when we will have already covered that orthogonality part. So here, third part of fundamental theorem, it is saying that if you are having a subspace, then subspace, and definitely if that subspace would have a basis, then that basis can be transformed into orthonormal basis u1 u2. So whatever basis it would have, so here row space of A, that means column space of A transpose, it is a two dimensional subspace. So any basis if you take, then any basis will contains only two basis element, and suppose this v1 v2 happens to be non-standard basis element, then apply Gram-Schmidt orthogonalization process. That means G S O, and with the help of that you can always convert this v1 v2 into u1 u2. And what is the property of u1 and u2? So u1 u2 happens to be orthonormal vectors. So that's where this is talking about the third part of fundamental theorem of linear algebra. And null space of A, it happens to be a line. That means it will have only one basis element, call it v1. So easily you can convert by normalizing you can get u1. So just normalize it and get u1. So even you don't need to apply grammars with orthogonalization here. Just directly you will. It is a very trivial kind of result. And if you are willing to see the pictorial version of this fundamental theorem, this part, several part of fundamental theorem you can look into here. Suppose this V, that means it is your row space of A transpose, row space of A, that means column space of A transpose. So that means it is a plane, and that what would be orthogonal complement of this row space of A? It would be null space of A. So here null space of A, you can observe that it is a line, and column space of A transpose, that means row space of A, it is a plane. Similarly, if you observe, you are starting with, you are taking null space of A transpose, it is happening in domain. This one is happening in domain. You visualize fundamental theorem in domain. Now here you visualize fundamental theorem in target space or codomain space. Okay, so here null space of this A transpose, and then what would be orthogonal complement of that? It would be column space of A. This is a total visualization of fundamental theorem of linear algebra. You can visualize all those part one, and then part two and part three. Everything you can visualize it here. Okay, this one was the story of fundamental theorem of linear algebra. Now we are coming to discuss about orthogonal transformation, and I had already mentioned that orthogonal transform it preserves orthogonality of vectors. Even something more than that, you can say that it preserves angle. So that means orthogonal transformation is a special kind of linear transformation which preserves uh, distance, that means the length of the vector, as well as angle of the vector, angle. So it preserves both kind of things. So that also, by default I haven't written that angle part, I have written just length part. Angle part easily you can derive it. It is a very easy result. So if you are having a orthogonal transformation which preserve the length, that means if you are having an orthogonal transformation, definitely it will preserve the length. So this one also it is taking as a definition, and this one easily implies that angle is also preserved between any two vectors. So under orthogonal transformation. So if you are having a orthogonal transformation, then always you can find a matrix, and that matrix also happens to be orthogonal matrix. The matrix of the orthogonal transformation happens to be orthogonal matrix. So right now this one is a concept. In next part we will discuss about how to find that matrix, that orthogonal matrix. That means when we will have orthogonal transformation, we will try to find matrix of the transformation, and whenever we will get that matrix would happens to be a orthogonal matrix. So here I have taken one example. We are considering an orthonormal transformation Rn T from Rn to R, and if you are taking any two vector V and W, and the angle between V and W are 90 degrees, that means orthogonal, then definitely the corresponding images would be also orthogonal. And proof is very simple. You can look into here. So that means proof is what does it means? That proof try to establish length preserve, that means it preserve the length as well. So that's this relation directly we are getting. That means here you can observe that TV satisfies Pythagoras theorem. So Pythagoras theorem is also very important in the case of establishing orthonormal or orthogonal transformation. So simply this proof is in last class I had already this in detail. So I would like to go another example. In reflection also I had already discussed. So all these are part of recap. So reflection with respect to subspace, as an it would be an orthogonal transformation. So if you are having a subspace in Euclidean space Rn, and you are defining reflection with respect to that subspace, that then that reflection transformation always happens to be an orthogonal transformation. So proof is again so you are defining reflection transformation like this way. So definition is very much clear, and geometry you can look into here. So this one is your x given vector, any arbitrary vector x, and reflection of x with respect to this subspace. I have taken a subspace as a line. It is a line. So reflection of this x with respect to this line is what? This is the reflection. So this reflection you can define as how? So you know that this one is the projected part, this one is the perp part, and if you take in total this one is talking about twice of per part. So from the picture easily you can derive that reflection of x, it can be written as a difference of projection minus x per. So this is the definition of reflection, because this one is x per, it is coming. So if you take 180-degree rotation, then this would be negative of x per. So reflection would be what? It would be this projection part plus negative of x per. So directly you are getting reflection of x. So this is the definition of reflection with respect to this line, given line. Now, if you try to establish that this one is a orthogonal transformation, so you have to take any arbitrary element x and find the norm of p of x that would be equal to norm of x. So here it is already, the relation is already established here. So it simply says that reflection is a orthogonal transformation. Reflection with respect to any basis is a orthogonal transformation. So one example of orthogonal transformation it was. Now, one more property I will talk about. It is saying that it is talking about relation between orthogonal transformation and orthonormal basis. It would help to find matrices of that. So if you are having a orthogonal transformation T from Rn to Rn, and then what we will observe that then definitely Rn will have a several bases. So among the several bases, most easiest basis is what? A standard basis. So take a standard basis whose basis element happens to be E1, E2 up to En. So what you do, find, because you know you are having given transformation T that happens to be orthonormal, and also you know about basis, a standard basis. You don't have idea of another other non-standard basis, but definitely you will have idea of a standard basis. Always you will have idea of a standard basis. That means you know about E1, E1, E2, En. E1 is what? 100, and E2 is 0100, like an En is 000, and last entry would be 1. So you know about that. So you have this one, you have this transformation, then easily you can find images of the corresponding standard basis element. And if you consider so again this would be n-dimensional vector. So if you consider this vector, this again happens to be orthonormal to each other, but these are not a standard basis element. These are very important kind of vectors of Rn, which happens to be orthonormal. So these T of E1, T of E2, T of En, it is forming an orthonormal basis, which happens to be a non-standard basis. So easily you can get a non-standard orthonormal basis from a given orthogonal transformation. So remember that if orthogonal transformation is given here, then easily you can construct a orthonormal basis for given Euclidean space Rn. So with respect to this orthogonal transformation, if you don't have that idea, so one approach we discuss about Gamma Smith. Another approach is this one, but it is highly dependent on the given orthogonal transformation. So little bit tedious job, you can say that. Unless that means suppose you are having reflection, then with respect to reflection, always you can get a what you can get a orthonormal basis. So here one example you can see here in R2. So in R2, what is the standard basis of R2? So a standard basis of R2 is, it is containing only two basis element, because dimension of R2 is 2. So it is having two element. One is E1, that means 10. What is E1 here? 10. And E2. E2 is what? 01. So find the image of E1 and E2 under this orthogonal transformation. T is a given orthogonal transformation, is from R2 to R2. Definitely it would be given here. When you are trying to construct a orthogonal basis with the help of orthogonal transformation, then T must be given here. This one is E1, this one is E2. So here you can observe that E1 has been mapped to uh, T of E1 and E2 has been mapped to T of E2. And you again observe that what was the angle between E1 and E2? It was 90 degree. And what is the angle between T of E1 and T of E2? It is again a 90 degree. So again we observe that a non-standard orthonormal basis of R2 whose first basis element is what? T of E1 and second basis element is T of E2. So this is another approach to find orthonormal basis of a given Euclidean space or given vector space. So this is the story. Now, so if you are having n by n matrix and we will call that matrix orthogonal if its column happens to be its column forms a orthonormal basis of Rn. That means if you are here, you have already received a orthonormal basis of Rn, and what you do, form a matrix whose first column. That means you are saying that A is a matrix of the given orthonormal transformation T or orthogonal transformation T. So A is a matrix of given orthogonal transformation T, then definitely you can say that it is a orthogonal matrix. So remember that here this matrix we have already calculated with the help of ascending basis. So we are getting this is the orthonormal or orthogonal matrix. So further, one more property you can talk about, if you do product of two orthogonal matrix, then the resultant, that means product AB, it would be again a orthogonal matrix. That means product of orthogonal matrix is again a orthogonal matrix. Similarly, if you find inverse of a orthogonal matrix, it again happens to be orthogonal matrix. And in case of inverse of orthogonal matrix is what? It is nothing, just do transpose of that matrix. So that means A inverse would be nothing, just it would be A transpose. So just do transpose and you will get inverse of that matrix in case of orthogonal matrix. So this product picture I have already given here. So orthogonality always preserve length as well as angle. So one more property that with respect to that finding inverse or transpose, what is the relation between inverse and transpose of a orthogonal matrix or orthogonal transformation, that I have already described it here. So we are taking the orthogonal matrix A, having these are the entries, this is the given matrix, and you just do transpose, then you will get A transpose. Then I would like to say that if because easily you can establish that this A is a orthogonal matrix because the column happens to be orthonormal vectors. So that's why A is a orthogonal matrix. Now we will see the relation between A and A transpose. So if you multiply A with A transpose or A A transpose with A, then what would be resultant? Resultant would be identity matrix. So it simply says that what does it say? It simply says that inverse of A is the A transpose. What is meaning of identity? Multiplicity identity. So if you multiply two number and it is giving one in case of a scalar, then we see that B is the inverse of A. So then in that case we are writing it B is what? A inverse. Remember that A and B must be non-zero. So that criteria. If it is zero, then 1 by 0 is not defined. You know that. From high school, it is very much clear. 1 by 0 is not a number, real number. It is infinity, we are saying. So simply it implies that A transpose is what? It is talking about inverse of A, provided the matrix given matrix is orthogonal. So easily it is very easy to find. So that's where there is equivalent definition of orthogonal matrix. So if you are having a n by n matrix, and the matrix we will call it orthogonal matrix if we multiply A transpose with A or A with A transpose, and then resultant is coming as identity matrix, or equivalently we say that A transpose is the inverse of A, and simply we can say that that matrix would be a orthogonal matrix. So it is another definition of orthogonal matrix. So this result you can observe it here. So if you suppose you have already taken A as an orthogonal matrix and you multiply A transpose with A, so that means this is A transpose and this is A. So this is the resultant. So you know that here A is a orthonormal matrix, orthogonal matrix. So what will happen? So column happens to be orthogonal factor. So v1 dot v1 it would be what? This will take value 1, and v1 dot v2 it would, what would be product? It is different, so it will take value 0. This one would also take value 0. Similarly, what would be v2 dot v1 dot product of v2 with v1? It would be what? It is 0, and dot product of v2 with v2 it would be 1, because all these vi's happens to be orthonormal. So that's why v2 dot v2 it would be 1, and v2 dot vn it would be again 0. And likewise you will get in last row vn dot v1, what it would be? It would be again 0. vn dot v2 again it would be 0, and vn dot vn what it would be? It would be unit 1. So in that process, what kind of matrix you got? So along diagonal entry happens to be 1, and off diagonal entries are 0. So that means that it is a identity matrix. So easily you can establish that. Remember that if your matrix is orthogonal, then A transpose A would be always a identity matrix. And similarly, if you can also establish relation for this general form, A into A transpose would be also identity matrix, provided that your matrix is a orthogonal matrix. That means columns are happens to be orthonormal factors. So then you are getting this kind of pattern. Now coming to find matrix of orthogonal transformation, how to find? So especially I came with this idea that why? Because finding matrix, we are trying to find matrix of a given transformation with respect to explicit form of transformation and with respect to basis. Now we don't need those things here. Here we are having facility of constructing orthonormal basis. So with respect to orthonormal basis, easily we can get matrix of the given transformation, or orthonormal transformation or orthogonal transformation. And there I will talk about one more concept. So here first I am talking about the matrix of an orthonormal or orthogonal projection with respect to a subspace. So consider a line. If you're saying a line, then definitely it will have only one direction. So easily you can convert v1 into orthonormal vector u1, because there is only one vector. u1 is the direction of v1. So this one is a line, and we are taking any vector from Rn, any vector x from Rn. Then we project this x over the line. This is the projection of x on the line. This is the projection vector. Okay, and u1 is the unit vector in the line L, or you can simply say that u1 is the direction of line L. Now, how can you find the matrix? Also, this projection is a orthogonal projection. It is a matrix, or it is a linear transformation. So if it is a linear transformation, our job is to find the matrix of that linear transformation. And we will see that how easy to find linear transformation with respect to orthonormal basis. So the projection of x over a line, it can be written as u1, this dot product x with u1 in the direction of u1. And what we know, that a dot product is always a scalar quantity, so you can write in left or right, you know. So c time a vector equal to v into c time. So a scalar you can write in left or right, there is no it won't affect, result will be not changed. So that's why I am writing u1 times dot product of, or inner product of x with u1. Now recall the definition of uh, dot product. So always we can write dot product how? So you can write it u1 transpose x. So dot product of x, I had already if you are taking any two vector x and y, what is the dot product? So dot product also you can write in the term of projection or transform, like you can write it x transpose y, or it is simply you can say that it is a matrix kind of definition. or you can write it y transpose x. Why? Because inner product or dot product is commutative, that whether you take it x transpose y or y transpose x, both would be same. That means inner product x with y and y with x both are same. So that's where this property is coming. So here and now also, so it is one kind of vectors also happens to be matrices. So matrix product is always associative. So apply the concept of associative. So associative means just you are playing in the product of matrices. You are playing with brackets. So here bracket was between u1 transpose and x. Then here you shifted the pre-shifted the bracket and you are taking bracket u1 into u1 transpose, u1 transpose times x. So tell me what would be this? It is talking about what kind of product? This product u1 transpose x, it is saying that inner product. But if you take a product like this one, x into y transpose, what does it talk about? I had already discussed several times. It is talking about outer product. It is always giving a matrix, one rank matrix. So u1 uh, times u1 transpose, it is giving a matrix of the orthogonal projection, and this matrix would be one rank matrix because it is outer product of a single vector. So this directly, so through this way directly you can get matrix of the orthogonal projection. Here you can observe that you don't need to calculate all those images of basis element. Directly you will get matrix of the orthogonal projection with respect to a line. Easily you can get. So this one is a very easy job. Now I can generalize it. Suppose we are taking a subspace which is m dimensional. That means the subspace will have m number of basis element v1 v2. So these are non-standard basis. So again apply Gram-Schmidt orthogonalization process and convert that into orthonormal set of vectors u1 u2 up to um. So what we do, we will take any arbitrary vector x from Rn and we will project over or on v. So if you are projecting x over v, then projection of x over v, it is defined as a what? This like this way. This I had already discussed that linear combination of u1, u2 up to um, and where the coefficient is coming directly from the inner product of x with ui's. So you are getting, this is the definition of projection of x over v with respect to orthonormal basis. So it is little bit tedious job that you first have to convert your non-standard basis into orthonormal basis. So that is the task. So everything hidden is here. After that, things would be very simple. Now we are having a orthogonal projection. So we will find the matrix of orthogonal projection. That means we know that orthogonal projection, it is a transformation from where to where. It is a transformation from now Rn to V. This projection is a transformation from Rn to V. Okay, so we'll find the matrix of that. So we don't go for all calculation. So we are writing projection of x in the term of orthonormal basis elements. So again we do similar thing that we know that dot product, this one is the inner product, it is a scalar quantity. So we can do this kind of changes. So we can write it u1 times this dot product of x with u1. Similarly times dot product of x with and again to uh, express this inner product like this matrix product like u1 transpose x, and what you do, take x common. X is now here you can observe that to apply associative property of multiplication of matrices and take x common in right hand side. So x easily segregated in right hand side. In every term you can observe that x due to associative property of product of matrices, x has been segregated in right hand side. So take x common, and in what would be in this bracket we are having m number of outer product of ui's. So that means this one is talking about outer product of u1, and this one likewise it will go here. 3 dot would be there. That means uh, inner product of u2, outer product of u2 like outer product of u3, and in the similar fashion you will come across to see last term would be outer product of So this matrix you are getting, this matrix is what? It is a M rank matrix which is constructed by sum of outer product of U1, U2, and up to UM. So easily this matrix, if you try to look into, I had already discussed in QR factorization. Q is what? Q is the matrix whose column are coming from orthonormal basis. That constructed orthonormal basis. First column of the Q1 would be U1, second column would be U2, and likewise the last column would be last orthonormal basis vector UM, like this way. So this one is Q. Okay. So that's where you can observe that you just do a little bit adjustment. You can observe that. So this matrix M is nothing. It is talking about product of Q and Q transpose, where Q is a orthogonal matrix whose columns are coming from orthogonal or orthonormal basis. So easily you can construct. So through this, if you are having a subspace and you are projecting any vector over that subspace, then what is the criteria? Find orthonormal basis of that subspace and construct Q. Then also find Q transpose, and in that case, define M, it would be just Q into Q transpose. It would give your what? It would give matrix of that orthogonal projection. Easily you will get matrix of orthogonal projection. Okay, job is done. So I will take one example, matrix of an orthogonal projection with respect to a plane. So subspace is here a plane. So your question is that question would be like that: find the matrix of the orthogonal projection onto the subspace V of Rm. It is where basis of V happens to be U1 and U2. I have taken notation U1 and U2. It simply say that, what does it say? It says that uh, uh, orthonormal basis of V are given here. So U1 and U2 forming an orthonormal basis of V. Easily you can see that U1 is a unit vector, U2 is also a unit vector, and if you are willing to find dot product of U1 with U2, that would be 0, perpendicular to each other. And if you find a norm of U1, it would be 1, a norm of U2 would be also 1. That means U1 and U2 forming a orthonormal set of vectors. So if you find unit product of U1 with itself, what would be this? It would be 1. And similarly find inner product of U2 with itself, it would be again 1. You can verify those things, but I know that here U1 and U2 I have already verified this happens to be orthonormal, U1 and U2. So easily, so if I am asking what is the matrix of orthogonal projection, so easily orthogonal projection we are defining like this way. So matrix of orthogonal projection, it would be what? Q into Q transpose, and Q is what? First column will come from U1 and second column will come from U2, and just to multiply with the Q transpose, and the resultant is this one. So this matrix, this is the matrix of this orthogonal projection. Directly, you can see that it is very easy to calculate. Even you don't need to know as explicit form of the orthogonal projection. Directly, you are getting matrix. If you have idea to get orthonormal basis of that subspace, then easily you can get the matrix of that orthogonal projection. So one more concept I would like to discuss about another characterization of orthogonal complement. So we are, suppose we are having a subspace V as a column space of A, or you can simply say that image of A. So you can recall those four fundamental subspaces. Many names I had already discussed here. You can call it image of A, you can call it column space of A. So if you suppose V is a column space of A, and it definitely it is a subspace in Rn, then what is A? A is having m number of columns, is a matrix. So simply you can say that what kind of matrix it is? N by n M matrix, because all VI's are what kind of vector? All VI's happens to be n dimensional vector. So Vi belongs to Rn, so n dimensional. So that's why E A is what kind of matrix? A is n by m matrix. Then what we will observe, so we can see that v per that means orthogonal complement of v, it is directly coming from the definition. It is collection of all the vector which which are having orthogonality with respect to every element of v. Orthogonality, that means dot product of x with uh, any element from v is 0. So this is the definition of orthogonal complement. So just you can express this definition in the term of basis element of v. So easily you can express it. So here what v is infinite in number. So every, it is talking about every v from every element v from the subspace v, and it is a subspace, so it is having infinitely many elements. Now if you express this same thing in term of, because we know that any element of v can be written as a linear combination of basis element of v, so that's why this here now we observe only m number of dot product. Here it is, so this has been reduced. But it is also giving the same paper orthogonal complement. And further apply the idea of commutative property of inner product. So you can write it uh, uh, inner product of x with vi as inner product of vi with x equal to 0. That means here you are having m number of equations. And further if you simplify, express this, how you have express this, you can define inner product like I transpose x equal to 0. Okay, so now what does it talk about? It is just talking about null space of a transpose. So if you are taking V as a image of A, then if you have idea of orthogonality, if you have idea of orthonormal basis, then easily you can express V per. That means orthogonal complement of V is nothing. It is just a null space of A transpose. That means left null space. So geometry you can observe it here. One example I have taken. So suppose we are taking a matrix with a single column. So A is a matrix which is having only one column. That's why V is the column space of A. A is having only one column. Entries are 1, 2, 3. Then what would be orthogonal complement of V? Orthogonal complement of V, that means V per, it would be just null space of transpose of A. What would be transpose of A? A transpose, it would be what? It would be a row matrix. 1, 2, 3. This one is the column matrix. This one is the row matrix. Okay. So you got V per. So this is the geometry you can observe that. So in this one was the given V. It is a V was a line, and this V per, it is a plane.